Now, one thing that is important to understand from the Bayesian classifier is the Bayes theorem, which is described in this formula. Bayes' theorem states that the conditional probability of B given A can be calculated as the overall probability of B multiplied by the conditional probability of A given B divided by the overall probability of A. The derivation of the formula is beyond the scope of this class. We will just use the formula here. Applying the Bayes theorem, we can extend this formula to look like this. The conditional probability of the case belonging to the target class of Y, given that the predictor variables take the values of x1, x2, all the way to xk, equals to the overall probability of the target class multiplied by the conditional probability of the predictor values being x1, x2, all the way to xk, given the case belongs to the target class, and divided by the overall probability of the predictor values being x1, x2, all the way to xk. Well, that's a mouthful, but let's take a look at our example before, using the Bayes theorem. Using the Bayes theorem, we can find that the conditional probability of y equal to 1 given x equal to 1, which means that the customer is male, it can be calculated as the overall probability of y equal to 1 multiplied by conditional probability of x equal to 1 given y equal to 1. Divided by the overall probability of x equal to 1. Okay, let's compute it. So, the overall probability of y equal to 1 is 80 over 200, because 80 out of the 200 customers were buyers. The conditional probability of x equal to 1 given y equal to 1 is 30 over 80, because 30 out of the 80 buyers were male. The overall probability of x equal to 1 is 50 over 200, because 50 out of the 200 customers are male. If you do the calculation, you will get the probability of 0.6, which is exactly the same as our probability number in the earlier slide. If we compute the conditional probability of y equal to 1 given x equal to 0, which means the customer was female, we will get the conditional probability of 0.33 using this formula, which is again the same as the probability we got in the previous slide. This shows that the Bayes theorem works in computing the conditional probability. As we learned earlier, the Bayesian classifier is often not practical in real-world cases, because the chance of finding exact matches of the case being classified is quite low and would leave us with a very small number of matching cases for computing probabilities. So how can we adjust this technique to make it more practical in real-life cases? Well, if you take a closer look at the formula for the Bayesian classifier, you will notice that the formula assumes dependency between the predictor variables, which means that all predictor variables must take the values of x1, x2, all the way to xk simultaneously. This is a very difficult condition to meet. The naive Bayes classifier assumes the independence of predictor variables instead. The independent assumption is often not realistic or naive, hence the name naive Bayes. For example, one cannot assume that variables such as income and education attainment are independent of each other, because in most cases, higher educational attainment often translates to higher income. However, making this assumption would make the Bayesian classifier feasible in solving real-life problems. As you can see from the formula for naive Bayes, the only modification to the formula is the replacement of the conditional probability of the predictors taking the values of x1, x2, all the way to xk, given the class of y, with the multiplication of x1 takes the value of x1 given the class of y, multiply by x2 takes the value of x2 given the class of y, and so on. And in the denominator, we are replacing the overall probability of x1, x2, all the way to xk, taking the values of x1, x2, all the way to xk, with the probability of x1 taking the value of x1 multiplied by the probability of x2 taking the value of x2, and all the way to xk. While the independence assumption may not be realistic all the time, this assumption now allows significantly more cases in the training dataset to be included in the computation of the conditional probability. Keep in mind that business analytics or data mining is the process of uncertainty reduction. While the solution may not be perfect, the prediction it provides would certainly help reduce uncertainty for us, and is much better than simply taking a wild guess or saying, "How would I possibly know?" While the assumption of variable independence does not capture the possible interaction between predictor variables, this transformation of the Bayes theorem has proven to perform reasonably well in many real-life situations, especially when large data sets are available. But also due to the assumption, using naive Bayes to predict probability values directly may not lead to very accurate probability values, as you see in the traditional Bayesian classifier. But using the predicted probability to rank the cases in terms of their likelihood of belonging to the target class would actually lead to quite accurate results. This is important to understand because in a lot of the business cases, we do not need to know the exact probability of a customer purchasing a product. We simply need to know who are the most likely customers to purchase a product. Therefore, using naive Bayes for ranking the probabilities of cases often is a better and a more feasible practical use of the technique than trying to accurately predict probabilities. Now, let's take a look at an example to see how naive Bayes can be applied to a problem. In this example, we have expanded our business scenario in the previous example by including a second variable, x2, which is home ownership. So in addition to x1, sex, we now have two variables, sex and home ownership, x2. x1 equals to 1 if the customer is male, and x1 equals to 0 if the customer is female, and x2 equals to 1 if the customer owns a house, and 0 otherwise. So now with two variables, each with two possible values, we need to find the following four conditional probabilities. The conditional probability of y equal to 1 given x1 equal to 1 and x2 equal to 1. The conditional probability of y equal to 1 given x1 equal to 1 and x2 equal to 0. The conditional probability of y equal to 1 given x1 equal to 0 and x2 equal to 1. And finally, the conditional probability of y equal to 1 given x1 equal to 0 and x2 equal to 0 as well. Now let's compute the conditional probability of the first one, which is the conditional probability of y equal to 1 given x1 equal to 1 and x2 equal to 1 using the naive Bayes formula. In other words, we are trying to compute the conditional probability of a customer belonging to the purchase class if the customer is male and owns a home. Applying the naive Bayes formula, this will equal to the overall probability of y equal to 1 multiplied by the conditional probability of x equal to 1, x1 equal to 1, given y equal to 1, multiplied by the conditional probability of x2 equal to 1, given y equal to 1. Divided by the overall probability of x1 equal to 1 multiplied by the overall probability of x2 equal to 1. Now let's find the numbers. So for the overall probability of y equal to 1, that would be 80 over 200 because there are 80 purchasers out of the total 200 customers. And the conditional probability of x1 equal to 1 given y equal to 1 would be 30 over 80 because there are 30 male customers among the 80 purchasers. And then the conditional probability of x2 equal to 1 given y equal to 1 would be 60 over 80 because there are 60 homeowners among the 80 purchasers. Now for the denominator, the overall probability of x1 equal to 1 is 50 over 200 because there are 50 male customers among the 200 customers. And the overall probability of x2 equal to 1 is 100 over 200 because there are 100 homeowners among 200 customers. Now let's compute the result. The result would be 9 over 10 or 0.9, which is the predicted probability of a customer who's male and owns a house to purchase the product. This suggests that a male homeowner would have the probability of 0.9 to purchase the product indicating a very high probability of purchase. Now you can compute the rest of the probabilities in the same way. Please go ahead and compute them on your own and check to see if you get the same answers as those in the slide. As we discussed earlier, the predicted probability may not be entirely accurate, given the assumption of variable independence in naive Bayes. The ranking may be more useful and accurate. The ranking of the probabilities suggests that a male homeowner has the highest probability of purchasing the product, followed by a female homeowner, then by a male renter, and finally a female renter, who has the lowest likelihood of purchasing the product. As you can see from the computation, when there are many predictor variables, the computation can get quite cumbersome. Fortunately, all the computation can be done quickly and accurately by the computer, and we will show you how to do that later. So, this is how the naive Bayes technique works. A few key things to keep in mind about the technique. First, when faced with continuous or numeric variables, you will need to convert them into categorical variables, typically using the binning technique. Due to the data-driven nature of the technique, naive Bayes requires a large dataset to achieve reliable predictions. Small datasets are not really suitable for this technique, especially when you take into the consideration of data partitioning for supervised data mining. As the naive Bayes computation depends on the training data, having sufficient data in the training dataset is crucial. Since naive Bayes is a supervised learning technique, data partitioning is a key step in the process. As no candidate models of different complexity are created in this case, there is no need to use the validation dataset to optimize the model complexity. Therefore, only a two-way partitioning is needed for naive Bayes. One potential issue one may run into when using the naive Bayes technique is that sometimes a predictor category is so rare that it may not be present in the training data. If that happens, naive Bayes will estimate the formula to be 0 since the conditional probability involving the predictor category is 0. For example, if we are estimating the conditional probability of someone owning a Ferrari given that the person has purchased a vacation home, if no one in the training dataset owns a Ferrari, it will make the conditional probability 0 as well. The solution to this issue is often solved using the Laplace smoothing technique, which replaces the 0 probability value with a non-zero value. In most cases, it will be replaced with the number 1, which results in no effect on the computation of the probability. Finally, keep in mind that due to the variable independence assumption, the estimated probability may not be very accurate, but the ranking of the probabilities is likely to be more accurate. Therefore, using naive Bayes for ranking, for example, identifying customers who are more likely to purchase, would be a more fruitful endeavor compared to trying to predict the probability of purchase accurately. Now that we understand the concept of the naive Bayes technique, let's apply it to a practical problem. In this case, Sarah, an intern for the Institution of Public Policy in Washington, D.C., is trying to build a model to predict which individual is more likely to have income below the poverty level. The census data are used for this analysis. Let's help Sarah develop a naive Bayes classification model to classify whether or not an individual is likely to earn below poverty level income using the predictors whether the person is married, sex, whether the person is white, age, and whether the person has a college education. The target variable is poverty, which has the value of 1 if the person lives in poverty and 0 otherwise. In addition, please help Sarah score the individuals in the score dataset using the naive Bayes model.